I think we're recording now. Okay, so welcome back. We left off and we were just getting started with understanding unified shader architectures, and the evolution of GPU computing using those versus previous approaches, which was really an attempt to sort of trick the GPU into doing general purpose computing. Now, with unified shader architectures, in which we don't have separate vertex shaders and fragment shaders that are physically separated and physically scheduled, we have this general pool of shader cores that could be used for any task, either the graphics tasks as needed, as well as then computational tasks. That allows for a fairly more straightforward way of mapping this highly multi-threaded model of computation to these devices. And that large number of threads is ultimately why we care. And I talked about that, briefly on Tuesday. But this issue of just the computational density of the devices, because our graphics rendering applications will take as much floating point math as we provide to it, and we'll use it, and as much bandwidth as we provide for it as well. That evolution of just increasing graphics fidelity and the very clear, market segment to do an extremely good job in providing that type of hardware has also led to sort of a corresponding step-by-step evolution of our GPU computing capability as well. So it leads those companies to be in a pretty good position in terms of there's a captured market already for those who just need better graphics performance, and then you're getting in the HPC and research and other communities as well, you're getting really good compute performance back out as well, because ultimately the math is roughly the same. The same kind of things we are interested in doing for vertex and fragment shading and all the other shaders we have as well are we want really efficient memory lookups. We want to be able to do matrix vector multiplication as efficiently as possible. We want to have some ability to accelerate all those kind of trigonometric and other special functions. That same exact functionality that we need for graphics rendering. Well, the math is very similar. It's not necessarily exactly the same, but it tends to be a pretty good correlation between what the graphics hardware is already going to need to be able to provide better and higher performance graphics to what we can then get for higher performance general purpose computation. So it's not an accident that it evolved in that way, but it's something that we can really explore and understand that model of computation, some of the programming models associated with it, and understand why it is different. And what does this mean from assuming that you haven't already kind of understood to some extent how vertex and fragment shading works. We're just doing compute shading or just CUDA programming in this context. What are the implications of that in terms of how we write code, in terms of how that code executes on architecture? And I think it's a fairly straightforward advance of what you would have learned in a CPRE 381 type of course, and just to see what the evolution looks like and how it's different from both the scalar processor and the pipeline processor we talked about in 381, as well as some of the vector extensions we already talked about in 381. So this is where we left off on Tuesday, just looking at our first CUDA kernel. Some of this is really just syntax and plumbing, which itself is not necessarily that difficult or exciting. If you already do C programming and do C++ programming, nothing here is something you can't pretty easily pick up and handle. But these are the three things we tend to see in any given kernel, right? And we talked about this kernel as being somewhat analogous to a function in C, except it's meant to describe an entire thread's functionality, and it's written from a single thread's perspective versus a function that gets called from some other functions. The kernel, which again will look a lot like a function in terms of it has inputs, and it has kind of some of the syntax of what would look like a function call in C or C++, is instead written from that individual thread's perspective, and to the extent it's getting called, it's actually getting scheduled by a thread scheduler, and we'll talk about some of the mechanisms for that. So these are three features you see. So the first one is just syntactical. There's a tag associated with things being kernel functions versus traditional functions, because we can have both. This example shows a function also being called from within that kernel. The inputs to functions, such as they are, tend to be pointers because, again, it's written from a single thread's perspective. So we're writing this code, we're developing this code, and it's meant to be run thousands or hundreds of thousands of time with increasing amounts of parallelism. So it's going to do generally one task and carve out a piece of work for itself such that we can schedule them all independently and not have them trample each other and overwrite the data that other ones are other also operating on. And the mechanism by which that is done is that there is a scheduler mechanism, and it's going to be a hardware scheduler, some driver hardware interface of the type we were already doing for our labs, and it's going to have some assignment of indices to these threads. And if we talk about the difficulty of doing CUDA programming, syntax doesn't really, it shouldn't really phase us. I think, given what you've already learned in your prior courses, but thread bookkeeping and management is where the complexity, such as it is for CUDA, really lies. So in this example, it's relatively straightforward. It's not doing much. But in this example, we see that there is sort of an auto-assigned index that is kind of a built-in variable to the call of this kernel. We don't see that it's not declared as a variable elsewhere in the code. It's sort of a built-in to CUDA where we're specifying, in this case, in the x dimension, and it can be x, y, z, a thread index into a block of threads. And we use those built-ins, and they get assigned on a per thread basis to let us carve out a piece of work for that particular thread executing that kernel. And in this case, we use it to index into our pointers in memory. So that's why the pointers tend to be our input. So everyone gets the same base address based on our bookkeeping, however we choose to organize it. We then grab one, or it doesn't have to be just one, but one or multiple elements of an input array, do some sort of processing on it, whatever that may need to be. We do that in our C or C++ syntax there. And then generally we have some output of the thread as well. This type of approach is sufficient when you have, well, what I talked about on Tuesdays is kind of embarrassingly parallel type of application. Real world applications aren't so nice and clean, right? We have an array, we want to do processing on the array. Only for very trivial applications can we do a kernel that looks just like this and call it good. The example I'll show, and I already brought it up, it was at the first day of class, the vector addition example where you have two vectors and you just want to add them together. That's embarrassingly parallel in the sense that no matter how large your vectors are, element zeros can be added independently of element one, element two, element three. And so because of that, the code for vector addition, which is sort of the most basic CUDA kernel you'll find to look as for an example, looks basically like this. We can give it as many threads as we have data elements in the array. Each thread can just do a single addition. May still not be the most effective way to do it, but it's at least parallelizable in that sense. And then each thread then just outputs a result vector that adds its individual element of A to an individual element of B, and then reports the result C. Real applications, have some elements of parallelism like that, but tend not to look quite like that. We may need to do vector element by element addition as part of some other task, but there tends to be some data dependencies. As we talk about in 381, right? There tends to be some natural data dependencies in the code we tend to write. There's some parallelism we can extract back out. To be effective on a GPU like this, there has to be a significant amount of parallelism, but we tend to also have to worry about how do we synchronize our code. How do we make sure that the threads are working in a reasonable lockstep fashion at some level so that we get a correct result back out? We can have some elements that are as basic as this, and we will always have some aspect of these three syntactical features of our CUDA kernels, but there tends to be more needed than just this because it's usually not this simple in terms of what we're actually implementing here. But in terms of language extensions, that's all we have in terms of CUDA. So there's function qualifiers. I don't think they're terribly interesting just to specify whether this is a kernel function versus just a traditional function that's getting called. There's going to be all sorts of variable type qualifiers to specify a little bit more direct memory management than we would typically need to do for traditional C and C++, although that is also slowly changing. There's going to be a very un-C-like syntax for actually launching these kernel codes. That's a part that isn't, clearly C and needs a different compiler for, and we'll see how we actually tell the GPU to actually launch these kernels and allocate the threads. And then there's the built-in variables that we already showed an example of for the actual indices of the threads to allow you to write the bookkeeping code to say, okay, I have 100,000 threads. As this kernel is executing, which thread am I? Which one am I, and what is my particular task based on some bookkeeping? And if I were to talk about what makes this slightly challenging to do, it would be that last part there of just keeping track of what data is doing what, and getting good performance out of that scenario. So, what does the following code do? This is a very brief CUDA exercise, so take a moment. What does this kernel do? I guess it's not showing the rest of it. This is straight from the CUDA programming guide, which I mentioned on Tuesday. There are a large number of CUDA textbooks now, and they're all kind of, at least so far to my knowledge, they're all kind of okay, and they get dated pretty quickly. So the CUDA programming guide is still, I think, the best prime resource for learning this material. What does this one do? Yep. Yep, you're both correct. I would call it, element by element matrix addition. And even not knowing, all the exact syntax, you can look at that, and I think it kind of, in some sense, makes reasonable sense, right? That before the previous example was doing element by element operations on a 1D vector, where there was just a function that didn't have an actual definition there. And in this case, now we're actually having a two-dimensional indexing into an array. Passed as pointers to input of our kernel here, and we're using the .x and the .y built-in thread index variables to give us that result of grab this particular location in matrix A, grab the corresponding one in B, add them together, and store the result back out in C. And by and large, that is what CUDA tends to look like. Here, let me just briefly open up the built-in vector add example. For those of you who haven't seen this kind of code before, um, I'll try to zoom in a little bit here. As an SDK example, it tends to look. It's got a lot more boilerplate than you would not necessarily need. But we can certainly just look at what this looks like in practice, and there's a little bit of checking to make sure that we're not actually outside of our range, which is, I guess, that's always a good thing to have. But depending on how you write the code, you may or may not need that particular check. And in this case, it's going to be using the block index, which I'll talk about in just a moment. But it's effectively that, right? It is a function that is written from an individual thread's perspective. So if you were to think of it as just a C function, it seems like a very trivial one, right? What is the whole point of even having this as a function? It's just doing one little addition here. Why do we even do this? Again, it's written from a single thread's perspective, and then once this thing is actually set up, and there'll be some memory allocation. I'll talk about this as well, some data initialization, and eventually we'll get to the point where this is the sort of non-C-ish looking part of the CUDA extensions to C and C++ that we have here. We are actually now not calling this as a function in that sense, that vector add kernel there. We're launching it. Maybe that's a bit of semantics, but what it really is doing is specifying not just the inputs to the function, which again, in this case, there was an extra constant to make sure we don't go out of bounds, but otherwise we're just passing it three pointers as if it were a function call. We're then also specifying, and it's trying to be as clear as possible. These are not function inputs. Those triple brackets we have here next to the name of the kernel that we have. We are specifying then what is the actual layout of work here. What is the layout of our threads, so that automatic, part of the hardware scheduling process, that automatic assignment of those indices happen, and then each kernel, as executing as an individual thread on the device, know what piece of work they are responsible for. So there's our very basic first kind of CUDA kernel here. I had an exercise in mind, but I don't think it's terribly interesting. So most of our CUDA kernel, we don't have to do this exercise, but most of our CUDA kernels are going to have some block of code that ultimately looks like this to some extent. And truly, we are doing of the whole world of possible, signal processing and computing and decision making and other applications. The math isn't ultimately all that different, right? I mean, there's basic functions that we've become familiar with. There's linear and nonlinear transformations. There's trigonometry. The math has not changed in hundreds of years. It's just the order in which we're ordering the math. So from the C programming perspective, after you've done sort of the bookkeeping part of the code, that's the interesting part from the CUDA perspective. The rest is, CPRE 185, learning how to do C programming, and then all the things you've learned since then. That is still basically the same. Excellent question, Micah. We have to talk about that. So um, this part, though, how we actually choose, and I guess you could also argue this part here, which I haven't talked about yet, how we decide what that layout is appropriate is not an obvious thing. The nice thing is, if you do it quote unquote wrong, um, it's not wrong from a correctness perspective. It's more of an issue of, am I getting the right performance out of my device? Could I have done better in terms of taking better advantage of my GPU? Any layout within some defined upper limits is a valid launch of threads on a device, but there's tools and there's way to reason about your particular GPU you're launching on that allow you to figure out what is the right number. Part of this is going to be application dependent because part of this, and again, we talk about applications for which it's not so trivially parallelizable because everything is fully independent and it's just a matter of more threads the merrier. We have some levels of synchronization that are required. So part of it's application dependent. What is the right organization of threads so that I'm getting enough parallelism back out, but my code is still correct, functionally correct. And then the rest of it is, am I allocating a sufficient number of threads? And usually more is better, but we have to be a little bit careful about that. But am I allocating a sufficient number of threads such that I'm getting the most out of my particular device? Um, Arguably, a problem that gets harder as devices have scaled up in size and not easier. But there are more and more modern features that allow us to kind of multiplex completely separate applications on the same GPU. So we don't have to worry about ideally just one application at a time. We can have multiple things running as needed. So this issue of thread organization is paramount. Um, these pictures could all be three-dimensional, but it's just kind of hard to see what's happening when it's three-dimensional. So CUDA and the CUDA um, model of computation and this GPU compute model that we use today uh, cares quite a bit about thread hierarchy and how we organize our threads. So this first part of the picture I'd want you to look at is the bottom half here, which is our organization of an array of threads into what's referred to as a block. So Micah, this is starting to get to your question here, which can be one-dimensional, two-dimensional, or three-dimensional. So I think the correct way to phrase this would be thread arrays can be up to three-dimensional, so one, two, or three-dimensional. For that vector add example, one-dimensional might still make sense, although there are limits we'll talk about, because our data is one-dimensional. So if you have one-dimensional data, maybe it makes sense to have a one-dimensional layout of threads in a block. For the matrix examples, maybe it makes sense to have the thread layout be two-dimensional, because our data is two-dimensional. But we know when we talk about dimensionality of data, and I think we know this, right? Certainly from this class as well as from 381, dimensionality of data is a programming language and a mathematical issue, right? From an architectural issue, all of our data is really one-dimensional. Our memory is one-dimensional ultimately. So part of that, there's no obvious answer, but when we're doing linear algebra, doing image processing, thinking about our data as being two-dimensional is kind of a natural thing. Having it be represented as two-dimensional matrices is a natural thing. And so having our thread layout also be two-dimensional, I think is all just kind of a natural consequence of that way of thinking about our computation. Even if ultimately that matrix is just one large array as laid out with load and store instructions, accessing our memory. But at first glance, that's the initial way we start to organize our threads into what's referred to as a block. This is all very CUDA and NVIDIA specific terminology. AMD will talk about wave fronts and things like that. It's very similar. They're trying to adhere to a very similar model of computation here. There's then this second level of hierarchy in which we then take that individual block and have multiple copies of that block. And there's implications for this. It's not just a semantic thing here. But in this case, we can say this is our thread block, which each thread block is having a two-dimensional, and it's 4x3. Yes, that's completely arbitrary, but it's 12 threads in a block for this illustration. So there's a 4x3 array of threads. It could have been 12x1. It could have been 2x6. I'm running out of other interesting factors of 12. But there's some layout of threads to get to 12 threads in a block. And then we would have some sort of decision made in terms of how many blocks we have And that next level of hierarchy is referred to as a grid. That seems arbitrary, but it's not. Part of the architecture for how these devices are laid out, it's a little hard to visualize when we think of our SGP with just having the two shader cores. Once you get to a couple dozen, you have to kind of think about hierarchy for organizing things. Part of the organizational structure is having this block as kind of the individual unit of schedulable work. And that if we need more parallelism than that, if we have more work to do than that, we organize these blocks into these grids in which those blocks then are entirely independent of each other. And that requires a little bit of extra thought. So you'll see a lot of the very basic examples in which the block layout will be sort of interesting in terms of two-dimensional for matrix, one-dimensional for arrays, for 1D arrays, vectors. Thank you. And then you'll see just the block or the grid size is just a scalar 1 because the complexity of adding that second level of hierarchy grows quite a bit. But to really take advantage and to get the maximum amount of threads on a device executing concurrently, you do need to do that second level of hierarchy. So this question on this slide is entirely rhetorical. But so you have this idea where you're launching a kernel. And if we look back at the syntax, and I'll bring it back up on this slide, or I'll bring it back here. We are now launching this kernel. So vector add was the name of the kernel in the code there. And those are actually the two parameters we're specifying in these weird triple bracket syntactical things. The first one is the grid dimensions, that top level part of that picture. And the second one then is the block dimensions. So you're specifying kind of that two layers of hierarchy of how things are going to be organized in terms of threads. It seems arbitrary, and maybe it is a little arbitrary, but the distinction between the two is as these are going to get mapped to our hardware, and I will talk about this more. This is the whole point of this lecture, so we're gonna get to this point in some level of depth here. As you're organizing these threads, as they're being executed on the device, it's done on a block by block basis. So we have this hierarchical layout of hardware and this hierarchical layout of threads. And the blocks on a block by block basis are going to the hierarchical units in our architecture. And then from within the blocks in a grid, it's who's ever next up gets then scheduled. Whenever the next hardware hierarchy is available, the next available block then gets scheduled on that particular hardware unit there. In this case, if we go back to this example here, they're both specified as integers, so they're just the one-dimensional case, which is also pretty common. In this case, this is given as a pretty common constant you see in these codes, but 256. So in this case, if we were to visualize what's happening in this vector add example, the thread block is this 256 long array of threads. And then in this case, it's actually divvied up by the total amount of elements in the array. So the math is something we have to do in our head. It's also a reasonable way to do it. So in this case, if there's 50,000 elements in the array in this code, we're taking that and we're dividing it by that 256. So we're basically rounding up here in this case and saying we have 50,000 pieces of work to do. Each of our blocks is going to handle 256 of them at a time. So we want roughly the ceiling of 50,000 divided by 256. And that's what this integer works out to be. That's also just a one-dimensional layout. Long story short, and I don't think you're going to find easy, obvious answers to this general question of how do I organize 1,024 threads? How do I organize 64K threads? The answer is it depends on what you want to do. It depends on some of the hardware restrictions. So there will be. There's hard upper limits on how large a block can be. And there's upper limits on the dimensionality in any of the dimensions for block size and grid size here. But it's also a function of what kind of parallelism your application has. For vector addition, it doesn't matter, right? And for matrix addition, it doesn't matter. It's all entirely parallel. Any block and grid layout will work roughly the same from a performance perspective. Real world applications don't have that much nice clean things. So while we can assume that all these threads inside a block are executing in this parallel mode, the blocks themselves are executing parallel to each other, but they're also entirely independent of each other. So the implications of having a larger block and a smaller grid size versus more blocks, but each block is smaller, or increasing both parameters here, really depends on how you're going to do that allocation of work and what is a reasonable way to partition the work. So that's why it's a rhetorical question. How do you organize 1,024 threads? Well, who knows? It depends on what your goal is. Um, if all the work is entirely parallel with each other, it doesn't really matter how you organize it. It has to do with the structure of the data you're working with, how you can write a kernel from a single thread's perspective, and managing the dimensionality of your thread layout. Because I will certainly say, if you do it enough times, you'll figure out certain cases. But that's actually kind of a pain. I mean, we go back to this previous example here, thread index.x and thread index.y. Okay, that's two dimensions. It seems okay. If each of the thread arrays can have a .x, .y, .z, that's thread index into an individual block. We're also going to see block index .x, y, z. That's actually a 9-dimensional layout, then, right? You have 3 dimensions of 3 dimensions. That's nine. That's not 6. That's 9 dimensions that you would potentially have. Starts to get a little hard to visualize, right? What does it mean to have 9-dimensional data and 9 dimensions of thread parallelism, and how you keep track of all of that? Um, that is the challenge of doing it. It's the thread bookkeeping, but it's also the way you reason about the problem. Getting to your question about the maximum number of threads in a block, it is. Let's talk about in a minute how we do that. Um, Getting the most out of modern GPUs while still maintaining compatibility with older ones. Yeah, and modern GPUs have kind of a nice trick for that as well. So in professional applications, what you will see is a lot of uh, initial kind of uh, device querying code, kind of thing that Intel bakes into their compiler when you generate assembly, which is a lot of check which CPU ID I have and emit these instructions if it's got this feature, or don't emit these other instructions if it has this feature. Part of that is part of the CUDA API itself. So you will see a lot of basically checking what device I have. They have CUDA compatibility modes, which tell you what features and the size of a particular device. So you'll see a lot of that code early on in the kernel, or before you launch the kernel, saying, "Okay, what am I running on?" And there's now like 8 different major versions of CUDA compatibility. So there could be a lot of that code to do that kind of checking. And then separately, also, I mentioned it briefly on Tuesday, and we'll bring it up again here. The actual output of the compiler when you're doing your NVCC versus your GCC is actually this kind of virtual ISA, this PTX encoding of the assembly instructions. And that actually gets further compiled just in time to actually run on the device. And that's, at least for NVIDIA's case, closed source to binary blobs that do that compilation or that translation from PTX assembly to the native assembly actually to run on that device. And that also can be done based on a query of device capability. Does it support this instruction? If so, emit this code, otherwise emit this code. Do other sorts of performance trade-offs based on what it knows about that particular device. But I would agree though that when doing GPU computing, when doing CUDA programming, again the C isn't any harder, and so it's very straightforward. And there's Python bindings as well, right? So if you don't want to mess with that, but trying to get the most out of your particular device requires understanding the actual features of the device at a level we tend not to ever think about, right? When you're writing general C++ code, it'd be nice if you think about cache effects, but you generally don't. It would be nice if you do, but we generally get by and trust the compiler to take care of some of those things for us. We certainly, I would say, don't think all too much about, you know, does my code lead to too many registers getting allocated? Um, at least I don't think in those terms when I'm just writing C code. When you're doing CUDA, again, you don't have to think in those terms. But if you'd like to get the most out of your device, you go back to kind of sort of dropping down into assembly ways of thinking, level of thinking when you're trying to optimize your code. You want to ideally get as many threads as possible allocated on the device at one given time. That's not always the case, but that's a pretty good rule of thumb. The more threads, the better, and we'll talk about why that's the case. But At a hand wavy perspective, it makes sense. More threads, more parallelism, more work getting done in one block of time. And to do that, if we care about squeezing performance, we do tend to have to drop down to that level of abstraction, which you may have thought you were done with when you took through 381 and passed that class. But that happens again for doing CUDA programming. So I already mentioned this, that we have the embarrassingly parallel applications, but those tend to be artificial ones. Real world applications have regions of parallelism and regions of sequential nature as they're executing, or they're partially parallel, in which there's blobs of data that can be operated on parallel, but not entirely so. So real world applications have to share results from one step of computation to the next set of computation. You can just think of that in terms of data dependency. Um, or just think of multiple steps of operations. Yes, the individual matrix addition is embarrassingly parallel, but then if we need to take the result of that matrix addition and do something else with it, there's a data dependency between those two steps. So parts are parallel, but the entirety is generally not entirely parallel. So we have to have some mechanism for code synchronization. So this was a CUDA design decision that, for the most part, has not changed from the initial design and release of it. This idea we are organizing our data in these thread blocks. By and large, the only synchronization you can assume is between threads that are inside an individual block. So to go back to that question of, how do I organize 1,024 threads? It depends on what amount of synchronization you have. Does my organization require that basically every 64 threads need to be in a cluster and coordinating with each other? That's probably going to strongly influence your block size. And then, if in theory the more the merrier, maybe your grid size is then correspondingly quite large. So, by and large, this layout assumes some coordination, and it tends to be actually a pretty tight coordination amongst threads inside an individual block. And for these blocks inside our grid, you have to assume, or one can assume as they're executed, they're completely independent of each other. That we can't know what block 00 will have essentially no knowledge of what block 1 comma 0 is doing. And in fact, there's no guarantee they get executed in any particular order, or on what region of the device they're going to ultimately get scheduled and executed on. So that will influence your thinking. I think part of the issue is, as we discuss this, that all sounds a little abstract, and that's my hope for next week, that we can dive a little deeper into a couple more realistic looking applications to see what this looks like in practice. Um, but that's the design philosophy of CUDA, that you have this two level hierarchy of thread organization, ultimately 9 dimensions of freedom, 9 degrees of freedom in terms of how you lay out the coordinates of your threads. But it's that lower level hierarchy of which you can assume some level of coordination, and at the next level you can't. And likewise, if you need to have inter-kernel communication, one kernel, this is slowly changing, but one kernel finishes, and then we need the results of that to launch to the next kernel, we generally have to assume that the entirety of the first grid of kernel blocks, of thread blocks in a kernel, are completely finished before we would launch the next one. That is slowly changing, but if we need that level of synchronization, that's the general data dependency graph that we wind up building as we're scheduling for our CUDA. So some of the terminology, which has also changed over time. So um, you can blame NVIDIA; they do keep changing some of the acronyms, but it's referring to the same general concept. So streaming multiprocessors is the higher level organization of cores. So the GPU streaming multiprocessors, you'll see SMX depending on which generation you're looking at, or SM. Those are operating on our blocks at a time. So the individual blocks in our grid of threads is getting scheduled on the SM at a particular time. And we have no control over that. There's a reasonable assumption about what kind of algorithm would be used for block scheduling. There's no reason for them to do it randomly or anything like that, but you actually have no direct control as a programmer over how that scheduling is happening. There's some driver hardware interfacing, like everything we're doing, right, in terms of how that scheduling happens. So in terms of the organization of what I'm showing on this slide, this is a very higher level view of that layout, right, where we have a layout of two-dimensional layout of blocks of threads. We're not actually showing the individual block arrays, but you can imagine each of these blocks has its own one, two, or three-dimensional layout of threads in the array inside each block. In this case, we have 8 blocks of threads. And we have a device, very basic GPU, that has two SMs. That's what proc0 and proc1 are referring to here. So that is the basic scheduling level of architectural detail there. You have these SM, these procs, and this is device 0, so GPU 0. And these blocks will get scheduled on individual SMs on a block by block basis. There's no, I mean, we don't have enough knowledge to know exactly how many blocks are getting scheduled at one particular time. We just know it's getting scheduled on a block by block basis. There's other things we can learn about our individual kernel that'll give us a better hint in terms of how that scheduling is going. In general, we don't get that level of detailed feedback back. You have to use a simulator if you want to know exactly how those things would be scheduled. We also don't have any guarantee on the ordering of those blocks. So this would be showing sequentially that we're getting potentially block 0 and block 2 being scheduled on SM0 and block 1 and block 3 getting scheduled on SM1. Um, I think we have some reasonable guarantees that both SMs are going to get used. We have no guarantee about what percentage of blocks go on which SM versus another. Presumably, there's some scheduling fairness algorithms baked into those schedulers, and you can act accordingly or design your code accordingly. Um, There'll be a certain number that can execute on the SM at any one given time. And so, well, with 8, it's not all that interesting, but we have 0, 1, 2, 3. Block 4 is going to get scheduled as soon as one of these blocks is finished. That can be the assumption we would make here. Which one gets finished first? We can't necessarily guarantee, right? The threads or the kernels are written from an individual thread's perspective. They should be executing roughly at the similar pace to each other. They're doing the same work because the kernel's written from an individual thread's perspective. But depending, and we do allow for branching and things like that, depending on simple branching conditions, depending on if we did anything that, if I'm block index 47, or if I'm thread index 47, I need to do a little bit more work here for my kernel. They won't execute at exactly the same time. And there has to be tiebreakers anyway, because if they're all trying to access memory at the same time, the requests are ultimately going to get serialized. And so some threads will just by nature complete earlier than others. Some blocks will complete earlier by others. They execute in roughly the same amount of time, but we actually don't know which block is going to get executed next. I think we can assume it's block 4, but we don't know that for certain. And we don't know which SM it's going to get executed on. Long story short there. But this also allows for our code as we design it once, as we compile it or design it once, to then potentially scale to different GPUs as we go. So maybe we test on a certain size and certain class GPU, and then later we then port it or just check the performance of it executing on a larger GPU. So that's what device 1 is attempting to illustrate here, that um, maybe it's the same class of hardware, but it's the twice as expensive model and it has 4 SMs versus 2 SMs. And in that case, potentially, now all the blocks could be executing at one time. Because if the resource management is such that we can execute 2 blocks at any given time on our SM, if we had 4 versus 2, we can then, in theory, execute all of those blocks at one given time. Doesn't mean that this GPU is twice as fast as this GPU. Again, the partitioning of work into threads isn't always going to be equal. And as we share resources here, now we're ultimately still maybe competing for memory bandwidth and things like that. So it's not necessarily twice as fast, but in terms of the thread utilization, presumably there's twice as many threads that we can execute on this GPU versus on this GPU at any given time. That doesn't exactly mean twice as much performance. But as a first order heuristic, it's generally a pretty good thing to have. More threads, more work getting done, better utilization of off chip bandwidth and things like that. Probably better performance, but not necessarily linearly scaling as such. And I mentioned this briefly, but just this is straight from the CUDA programming guide. Um, this issue of coordination and cooperation between all the threads may require multiple kernel launches. Just like it makes sense to decompose our code into functions in the first place, given the parallelism of a particular application, it would require then multiple separate kernel launches to execute the code with some sequential and serial regions between that. So if this is our C program's execution from top to bottom on this picture here, this is showing generally how the execution would happen. There's always going to be the host starting off. So no matter what, there's a CPU in the loop somewhere that, if doing nothing else, is doing some memory allocation, thread allocation, and launching the kernel. That's our serial region. That all happens very serially here. So visualize is just one thread of execution to start with. We have our kernel launch, which in this case has a 2D layout of a 2x3 array of our blocks in a grid. We have to wait, presumably, we can also tell it to go free running. We have to wait, though, presumably, for the next collection of results. This kernel did its work, updated a whole bunch of values in memory. Host side code now should do something. Collect the results, combine the results, do some very simple transformation of the result. But whatever it is, there's a serial region there before the next kernel then would be launching, which would presumably be taking the results of the previous kernel and doing a further set of transformation for it. And it's hard to say outside of a very hand wavy kind of form why it would make sense for this first kernel to be 2x3 and the second kernel to be 3x2. It's very arbitrary, but one could imagine certain transformations in which that layout and different size thread blocks inside that grid may make sense from a programming perspective, from a parallelism perspective. But in general, it's something of a blank slate between these kernel launches. You launch the kernel, the real state that it's getting to impact that you can actually preserve between those launches would just be that global memory. And that's why these kernels tend to be written from the perspective of updating a pointer or updating the values pointed to by a pointer for our device memory. We can presume that as that memory gets allocated, and it's allocated by the host generally, copied over, the kernel operates on it. The host may then do some further copies, some further transformations, or just do nothing with it and wait for this entire kernel to be done. Then it can launch the next one, potentially passing it the same exact pointers for that second run, or different set of pointers. And it's definitely the case. Although we are writing C++ style code, there are more options. Just like in our OpenGL code and our GL shader code as well, where there's some value in being more aware of the different memory layout options. That is very much the case for our CUDA code, our compute kernels as well. From a layout perspective, it's not so different than what a traditional CPU's code executing on a traditional CPU would see from a memory perspective. It is a little different. So registers are still a compiler allocated resource for our GPU. It is different, but it is still allocated by the compiler. So you have C code, and it has local variables in your C code, and the compiler, just like for traditional C code running on a CPU, is going to allocate registers based on local variables. There's also still data cache and instruction cache, where generally as a programmer, there's good practices you want to follow for temporal and spatial locality. Yes, this is still relevant to us, right? But we generally don't have direct access in the kernel itself in our C code to impact our caches there. There are actual hooks for pinning memory and things like that that can impact cache. You can do that in traditional C as well. Then what there is, which is different, is for these individual SMs. This is showing it from a kernel's perspective, but also it has the architectural implication is very similar. There's also just a dedicated region of shared memory. And that is a separate block of memory of software allocated memory versus cache, which is this hardware managed memory. You can refer to it as scratchpad as a term that we see used in the embedded system context, but in the GPU context, we just see it referred to as shared memory, which is allowing us relatively straightforward and cheap synchronization amongst threads that are inside a single block here. So you can think of that as a software managed cache. It's going to be smaller for that reason. It's not hardware managed, so your data has to be in there if you want it, or you're going to get incorrect results. There's no misses in the shared memory. We allocate a block of it, we get pointers to it. Our code accesses that like any other array we have here. It's just going to be allocated into a physical region that is local to the individual streaming multiprocessor on the chip. And then finally, we have everything else that's fitting into our global memory, which is our what we would call in 381 our main memory. That part also has not changed. There's going to be layers of cache, presumably between our cores and our main memory. The only other wrinkle here is depending on which compute capability and which architectural generation you're talking about, that may be a uniform view of memory in which both the host, this is CPU here, and the device, the GPU here, may have logically shared and even in some cases physically shared memory between the two devices. But from the GPU's perspective, it's not so different. We have registers; those are compiler allocated and managed. We have now shared memory, which is a little different. It's a software defined region of memory that should be a good way to synchronize between threads, and it should be more efficient than going to the next layer of managed memory, which is our main memory, our global memory here. There are others as well. There's this concept of constant memory. Um, Very similar to like uniform memory for our graphic shaders. There's also very much still the view of texture memory. All of those texture fetch units, as we showed on Tuesday, they're still there, right? We still have all that functionality in the hardware for the graphics rendering. It's still available there for the compute side of things. But texture memory and texture fetch units tend to have slightly different rules associated with it. Now, if you're going to use that memory, it could be very effective for your purposes, but now when we're dealing with texture memory, we have to worry about textures. We have to worry about particular data layouts, um, aliasing rules, MIP mapping, and things of that nature. All that is still available to us as CUDA programmers looking at it from a compute perspective, but it's got all the challenges associated with dealing with texture memory, which is you have to be very hyper aware of the organization of the memory and how that data is going to be interpreted. It's not just a scratchpad memory. But if you do have a use case for that, and there's all sorts of examples that show interoperation between rendering code and compute code, then using that would be more effective than just putting everything as a big array in our device memory. From our lab implementation for our simple graphics processor, we're not doing too much with our texture memory, right? So there's a small advantage to our texture lookup versus a load store lookup for our SGP implementation, but it's a pretty small one, right? At least as driven by MP4 spec, and a couple teams are extremely close, and I can't wait to see it. Be very happy to see Dr. Jones' face on a triangle, so I'm hoping to see the first one, less so my own face. Um, the only advantage we are seeing would be a two-dimensional index baked into the instruction itself. So that would be more effective, right? Otherwise, you could always do it as a two-dimensional lookup into memory. So you have to do a read, a multiplication, an add, followed by a load instruction. Whereas mathematically, you're still doing all those things, but it can be done with a single kind of baked in instruction. So there's a very small advantage for us to be doing texture fetches, even in our own code versus just loads and stores. The same would be the case, except with all the other features that are generally supported for texture memory. If your application can take advantage of those features, it would be advantageous to to do so. So we'll start with a sample device here. This is our NVIDIA G80. So this is our initial Tesla class hardware, really our first one that allowed us to do CUDA programming in the wild. So this was originally 128 total streaming processors. And I think I was a little remiss in not directly defining that term. Let's go back to that real quickly here. Um, I said it very briefly. I think the marketing and the terminology is a little unnecessarily complicated. This top level organization, those are our SMs, streaming multiprocessors. Inside each of these SMs is a varying number of stream processors. To me, that's awful. I don't know. Streaming multiprocessors full of stream processors. I mean, what is a processor anymore? It just sounds like a nonsense word if you use it too many times. It's slightly improved, although it's also kind of a marketing thing where they are now referred to as CUDA cores. So if you see some documentation that refers to SPs and elsewhere you're reading about CUDA cores, by and large, those are exactly the same term. And you may see SMXs, you may see CUDA cluster also being used as that terminology, or SMs. That's the general two-dimensional layout. We have the smaller cores, you can think of them, our CUDA cores. These are our SIMD styles, 381 style, bonus point 381 style CPUs. Then they're organized in this hierarchy. That's our SMs. So I neglected to mention that. But if we go back to our initial so-called Tesla class hardware, that was 128 CUDA cores or streaming processors in our 16 SMs. So there was 8 streaming processors uh, per streaming multiprocessor. Life was a lot simpler back then. Current generation, at least based on what's been released in this past calendar year here, that's 10,496 CUDA cores in 82 SMs. Within the math is that divides by 120, 128 streaming processors per multiprocessor. Does this change how we want to write our code for CUDA? And then that was getting to a couple of the questions that we saw in the chat here regarding that. I think between first generation and current generation, the answer is yes, I think truly. But in general, it really depends on to what extent it's important for you to take advantage of newer features in CUDA, to what extent it's important to you to scale to the total number of CUDA cores or streaming processors that are available on the device. There's some compatibility, issues as well, but that's more of a implementation characteristic, than an actual logical issue. So the answer is yes, technically, but really in practice, only if you care about taking advantage of those newer features. Um, so that's a very nice aspect of CUDA and of this layout. Because going again back to this picture, yes, this is a much more simpler picture of scaling where we go from 2 SMs to 4 SMs. But at least in theory, assuming you have enough blocks to keep both devices happy, you'll get the second device and the potential parallelism of that second device essentially for free, assuming your code is written appropriately for the first device as well. Is that the case when you go from 128 to 10,496? Well, maybe not. That it's harder to write a piece of code that would scale to that level of difference. But within reason, the code will scale to larger devices, assuming you gave the older devices enough work to keep them fully busy. That scaling kind of gets baked into how the threads are getting scheduled. I personally think it's pretty fascinating, just those two, just chip packaging photos here. Uh, the G80, this is all just based on Wikipedia, is 681 million transistors versus the GA104 is 28.3 billion transistors. Well, 28.3 billion transistors is kind of mind-boggling in the first place, but actually they're roughly the same size. In terms of our actual package sizes, we've really been stuck in that same, 300 square millimeter size for generations and generations now. It's just a kind of incredible thing to me that part of it is the advantage of GPU technology, right? The layout is going to be extremely regular. Presumably, there's a little bit of copy and paste going on. Not to simplify the task too much, but maybe a little bit of copy paste going on. You design the individual SM extremely carefully, really conscious of routing paths and things like that. Presumably, it's a matter of fabrication feasibility to then decide. We have one that's designed extremely well. We can go to 2. We can go to 4. We can scale accordingly, kind of, sort of, as a copy paste operation. So part of that is the regular layout of a GPU. The larger ones are truly just more of the same of the smaller versions of the same class of hardware or the same technology generation at least. But even having said all that, it's amazing me to see that, given just we're not talking 60 years here, right? We're talking 16 years here roughly that we've been able to have that level of scaling in terms of our transistor density. Um, I guess it makes us feel a little bit more, meager about our own 2 CUDA core implementation for CPRE 480 here. Um, but still, it's an incredible kind of journey of what what your friends in the VLSI and the semiconductors, area have really been able to accomplish for us, right? Architecturally, of course, the things are still interesting, but a lot of it is still just kind of replication and just being able to do more of the same, taking what the VLSI folks have given us as a feasible design target and a power budget and all that kind of thing for the rest of the system integration, and then taking advantage of that. Um, that's a good question. NVIDIA doesn't manufacture. Well, it depends on what you mean by manufacturer. Um, very few companies actually fab chips anymore, right? There's like four in the entire world of a reasonable size. So NVIDIA is does not manufacture their own chips. They design the entirety of their own chips, and maybe it's a little bit of semantics in terms of who is manufacturing the chip. They have to have very detailed knowledge and have to work extremely closely with the companies who do actually do the fabrication. TSMC, by and large, Samsung as well does quite a bit of their fabrication. I don't think Global Foundries does any of their fabrication for Nvidia. So maybe it's a little bit of semantics to say Nvidia doesn't fabricate their own chips. Um, they have to have very in-depth fabrication knowledge to be able to design these chips. There is ultimately a handoff phase. They don't just send a zip file or something. There's a close collaboration there. But yes, it's another company who is ultimately responsible for fabricating those chips. Um, they also this has changed over time, but they also weren't always the primary integrator for their chips as well. That has started to change over time, but there was certainly a period of time where they would have their own graphics card implementations, and they'd be good reference implementations. But there was other integrators who would then be also responsible for doing that value add of purchasing GPUs, the actual chips in bulk, integrating them with certain GDDR memory and the rest of the system, and then putting that together as an entire package. They do most of the integration themselves now, so that's less the case. There's presumably some fundamental limitations of package size, which is why we don't have 10-inch size wafers. There's some instances of things like that, but part of it may just be manufacturing the actual silicon die and getting things to fit in a certain period of size, certain space of size. The larger it gets, the more likely there's to be defects, and the harder it is to actually get things to be um, to succeed in the actual fabrication step. So there's presumably a reason for that. Having said that, 28.3 billion transistors is an absolute ton, and the power consumption of that must be incredible as well. So um, there's also just some fundamental upper limits of that as well that presumably they're well aware of also. So I think we don't lose too much generality by starting and looking at the G80, looking at 2006, and just kind of briefly showing, as we started to do on Tuesday, how things have changed in the meantime. So this is the basic G80 architecture, and at its highest level, right, we did see this from the version of this same diagram from the graphics to compute view of the same hardware. This is another version of the same exact picture. These here, these individual boxes, I don't know if you can see my mouse cursor here. These here are the individual SMs, and they're labeled as such. And then inside each SM are 8 of these CUDA cores, or these SPs here. So we can actually, this is straight from your actually 381 textbook. You can actually blow up the individual SM to see what it's actually doing. So we have here, it's not showing registers and things of that, but it's showing some of the detail. We have the shared memory block I was talking about briefly before. That is local to the SM. So it's shareable amongst threads that are in a block that are allocated to this SM at any given time. That's thread issue, constant cache, which there isn't that much to say other than it's a custom piece of memory that's already quite useful for graphics applications for our uniforms and the like. It's also could be utilized by your compute code as well. You have your instruction cache. There would also be some sort of shared data cache as well. And then you have the individual CUDA cores or the streaming processors here as well. And these are going to be your fairly basic vector processors that are going to be able to handle a certain amount of parallel computation at a given time. There's also a certain number of these SFUs, these special function units, Those are the ones that cause us grief for MP3, right? Do I want to be able to implement exponential functions as a single instruction, or do I want to just encode those as software? Different classes of hardware, as evolved over the generations of technology here, have made there's been different design decisions made for that in terms of how many special function units there are, of what nature are certain things supported and other things aren't supported. Those would be shared amongst multiple things in the SM here. One takeaway from that is that those special function units, let's say sine of x, right, to calculate that, it should be faster, presumably, than a software lookup table or other type of algorithmic approach to calculating trigonometric functions. But it's not free in the sense that addition is effectively free in our SPs here. There's a lesser number of them, there are fewer of them on the core. They presumably then have some scheduling associated with them. We've seen a little bit of that, right, with our divider core. Dividers are significantly more expensive in terms of transistor budget than adders, and also as well as multipliers. So we can have an adder in our vector in our shader implementation in our lab SGP GPU, but we probably don't want to put four of them in there. That's just a trade-off we're making, right? That by if we were to put four of them in there, we could get slightly more parallelism out of our division operation. Well, division is not as common as addition, and not as common as multiplication, not as common as load and store. And secondly, by doing so, we could fit it, but then we could fit maybe fewer of these in total in our total chip budget. So you do tend to see this trade-off in modern GPUs, in which you have a certain number of these basic vector processors, not so different from what you've already been building, and a fewer number of custom accelerators for those more annoying but still occasionally necessary functions that we still need for correct operation and we want to make faster, but we can only allocate so many of those. That's a design trade off that presumably is heavily data driven on NVIDIA's part, um, based on the applications that not this generation's hardware is going to need, but maybe next generations or even the generations after that. Um, Talking to former students who are at AMD and are at NVIDIA, um, those design decisions get made significantly earlier than you think. So the folks at NVIDIA know what their GPU is going to look like 8 years from now already. Um, they haven't gotten around to building it yet, but they've made the projections. They have a feel for what scalability is possible. So that kind of analysis is what large swaths of the engineering workforce at those companies would be doing, based on understanding applications. What is the right amount of parallelism in these chips? And also based on technology feasibility. What's the next billion we're going to be able to fit? Or are we going to stop at 30 billion, or will we get to 300 billion? They have people who are capable of making those projections as well. But from the application side, how important is sine of x really? I know that's simplifying view, but how important is it really? Consequently, how many of them should we put on our chip? That should be made. Those decisions should be made in a data-driven methodology, understanding benchmarks, not today's benchmarks, but next generation's benchmarks, as best as they can be projected, and trying to map that to the performance of what your architecture would be able to support. And you can see that just by comparing the G80 architecture um, to a Kepler class architecture, which is also now kind of dated, but does show that evolution from first generation to third generation of NVIDIA CUDA compliant hardware. And what do we see here? Well, a lot more greenish boxes here, but basically the same thing is happening, right? Going from 128 CUDA cores organized in 8 SMs to I think it's 192 in this GK110. This is the hardware that's on your Xilinx boxes. This is why I brought this one out here. Otherwise, it's extremely similar. So you have the individual SM, which is being illustrated here, and there's more. There's more of those cores. That decision is something that's changed over time. How many cores in an SM? Um, the trade-off is how many threads you typically would see in a block would then influence how large your SM would be versus having more individual SMs there. But it's a lot of the same. So there's your data cache, there's your register file, and you then have certain units that are then your dedicated unit. Those are your SFUs. It's very tiny on this diagram. Um, and also this one in the second and third generation has separate double precision floating point unit versus the regular cores, which are single precision floating point units. From our perspective, our implementation, everything is everything is fixed point units, so we don't really play around with that trade-off very much in this class. I've certainly thought about it. What would be the downside of having this all of our hardware be floating point hardware in this class? Um, there's some advantages to floating point hardware, right? It's for single precision, everything is a 32-bit piece of hardware. That's a nice thing. So you don't have to worry about going from Q16.16 to Q32.32 and then truncating back down. I mean, there's some real value and advantage of simplicity of data layout for single precision hardware. But just each of those individual units, and we're talking about the adders here, not to even start with the multipliers and the dividers, are so much more significantly and complicated than the equivalent integer hardware. Um, Real code needs floating point hardware. So I understand why these are all floating point units here, but from a design perspective, in terms of the hours we have dedicated to this class, fixed precision or fixed point and using that precision, although we've seen the headaches involved along the way of underflow and overflow and truncating too early or truncating too late, um, it's probably still the right trade off in terms of being able to fit even what we have so far on the chip that we're using this semester. No pressure on the group to get the next device working here as well. Talk a little bit more about this SM or SMX architecture here. Again, so the whole GPU architecture is built around this idea of this scalable array of these multi-threaded CUDA cores or streaming multiprocessor SMs or SMXs. So you have your CUDA program. Host CPU is going to invoke that kernel grid, and then those blocks of the grid are going to then get enumerated and then distributed to the multiprocessors on the particular device they're being executed on. The threads of that individual block are going to be executing concurrently on just one of those multiprocessors at a time. And in theory, actually, multiple thread blocks can execute concurrently on the one multiprocessors. Only when that thread block terminates, when all the threads that are inside that block terminate, do we then launch the next one on there. And the idea is that these SMs are designed to execute lots and lots of those threads concurrently. How many is very much a implementation specific detail that you can actually query and see what is my upper limit for a particular application. But that generally at the highest level, that's what the SM is designed to do, to execute hundreds of threads concurrently. And it's a management problem at that level. How do you manage such a large amount of threads? This is where this concept, which is part marketing and part a slight technical change of, if you've seen the term, this SIMT architecture. Single instruction, multiple thread. I'll give you my basic definition of it, which I think you have to read through a lot of NVIDIA marketing to see what this truly means in practice. Just to remind folks, it's certainly been a while, we talk about very briefly in 381, depending on who you took it with, this idea of SISD is kind of the default scalar architecture. Single instruction, single data. At a time, we're worrying about one thread of instructions executing on one piece of data at a time. This kind of coarse high-level parallelism we tend to see in multi-threaded programs written on traditional CPUs is this MIMD, multiple instruction, multiple data. Totally different threads of execution operating on totally different streams of data. You have your 8 cores, you have 8 threads executing concurrently. We also talk a decent amount in 381 about SIMD as a microarchitectural optimization that allows for a certain level of parallelism. That is single instruction, multiple data. That's what our cores, at least in theory, in 480 this semester are implementing. Very similar to vector processor, there's a subtle distinction between a vector processor and a SIMD processor in terms of instruction streams. But in general, you have a single instruction at a time from a single thread of instructions, and it's executing on a block of data at a time, where block tends to be pretty small. So instead of a regular scalar add instruction in our SISD architecture, you would have a vector add instruction that would take 4 values or 4 pairs of values and add them together independently, or 8 or 16. It's at that level of parallelism. It's not you wouldn't have a 1024 block of data addition in a single instruction. So 4, 8, or 16, something of that level. That is traditional way of parallelizing on a data level. The SIMD approach is still, or excuse me, the SIMT or SIMT approach is still effectively just the same as the SIMD approach, which is you have these individual cores and they have that functional unit type of parallelism. The main difference, and again, it's part marketing, but it is an actual practical difference, is that you now have multiple threads that are all executing that same instruction stream in parallel as well. And that leads to potential real savings in terms of how you do your architecture, what simplifying assumptions you can make in your architecture. For example, although this has also been changing over time, in this SIMT or SIMT model, you can have, for example, 32 threads that are all doing that vector type of operation. And because we assume that everything is executing the same kernel, they can all share a program counter, for instance. And that leads to a significant amount of savings. And then consequently, the cost in switching from one block of, I gotta use the right terms, one grouping of threads to another grouping of threads is extremely low for this model of computation. Because if we can guarantee, certainly unlike in the MIMD case, if we can guarantee that all these threads are executing the same kernel, we can make certain design decisions that allow us to really minimize that swapping cost. Certainly, if they're all executing the same instruction stream, our instruction cache performance should be extremely good, right? Every instruction from the different threads is executing effectively in lockstep, and consequently, certain simplifying assumptions like having just a one shared program counter for a grouping of threads, having a very effective instruction cache. You'll see for GPU workloads, instruction cache hit rates of 99.8% is a very common thing. It's not an unusual or an outlier thing. The other design decision we tend to see is as we organize by these SPs on this SM basis, we can implement a really fast switching of threads by having a physical allocation of our register file that's extremely large. Whereas in traditional, MIMD parallelism, there's an actual cost associated with switching from one thread to a next. We have to get the current thread out of the CPU so the next thread can go. I mean, it's not this overwhelming cost, but we have to do work. We have to grab the state of that thread, copy to memory somewhere, at least the register state, and then copy the new one back in. Thread swap, context switch. Right? You learn about that in 308, at least I hope so. For this SIMT model, the design choice is to minimize that overhead as much as possible, that overhead of switching between threads. When you're having hundreds of thousands of threads, that becomes a critical design consideration. And the design choice we see is having a large, basically a massive register file. 65 or 64K registers per SM. That number has actually kind of grown and shrunk over time depending on the different design decisions. But for our Kepler class hardware, that's the number it was at. And what we have then there is for the block of threads that's executed at one given time on an SM, there's no context switching penalty at all. They're all running the same code. So within reason, we don't really need to keep track too much in the way of program counters. Certainly instruction memory, we don't have to keep track of. We don't have to flush caches or anything like that. And each thread still has its own register space. We still have to do register allocation in the compiler. You have variables that are local to that thread, and those are going to correspond to registers that are getting allocated. But we have a very large upper limit on the total number of registers available at one given time, and we just allow each thread to carve out a chunk of that register space. So when it comes time to go from one thread to the next thread in this SIMT model, the context switch is no more than just saying, you're next. The CPU is the functional units are yours to do what you need to do. Your registers are there. The next thread's registers are next to yours, and they're allowed to share. This also goes back to this question, and this will probably be a good stopping point for us today, certainly because we've kept going, is what sets that upper limit in terms of how many threads is the right amount? By making these kind of design decisions, which is to support thread swapping as quickly as possible, to have these blocks of threads that are that schedulable unit of work, when you have, this is a physical upper limit on the SM, the code that you write, and the compiler will tell you, you've written this code, we've optimized it as best we can, you have 26 registers that this is going to use. That will limit your block size. If you have 26 registers, and maybe that's not the number is not going to divide very well. If you have 1K registers, which would be a large number, then you could fit 64 threads at a given time, and not 65. And so you could not have a valid block size of larger than 64. Not normally your register count is significantly less, but still that fundamental decision of register usage as well as shared memory usage dictating how many threads we can squeeze on at one given time will then also dictate how many thread blocks we can have at one given time, which should then in turn dictate what is the right number of blocks to have, what is a reasonable organization. So when we talk about that bookkeeping code we tend to see at the beginning of our NVIDIA CUDA code here, it's in part to query that, to give us a good feel for my data size as well as for my GPU size, what's a good layout of my threads. More generally better, there's hard upper limits that are set by things like you have this many registers to play with. Each thread's going to peel off a few for its own. This will limit then how many we can have. We went a little long today. I apologize for that, but there's a lot to talk about here still. I didn't go to any of the demos I wanted to show today, but anyway, we'll pick up on this on Tuesday. I think it'll be very helpful to actually dive into a real CUDA application to see those design trade-offs in practice. The SDK examples are a little tricky for that because they tend to be written with portability in mind. So a lot of variably defined things, but we'll get a chance to play around with that and see what this looks like in practice. Um, Usually using the Kepler example as our main motivating architecture because that's what you have access to run code on, and you can run CUDA on those machines and play around with that. So we'll leave things here for today. Good luck on your projects over the weekend. I hope you're going to get right back onto it after class today. Thanks.